In this video, we're going to develop a tool that we can use to identify whether an amplifier is stable. This tool, called phase margin, is very practical and easy to measure in lab, but we make a few approximations to get it. Don't forget to use it in conjunction with other stability analysis tools like root locus, Nyquist plots, or common sense, just to account for those approximations. One of the first challenges of analyzing the stability of amplifiers is deciding what stability even means. The typical definition given in controls classes is bounded input, bounded output stability. However, all outputs from circuits we've seen are bounded by the supply rails, so that definition loses some steam for us. Fortunately, however, our linearized small signal model holds when our output is far from the rails. So one of the conditions that we use to assess stability of linear systems, one of the things that sort of led to bounded input, bounded output stability, is still useful to us. And specifically that's watching out for poles in the right half plane. Poles in the right half plane probably still mean our amplifiers are going to be unstable. We just don't know how to define what unstable means yet. And that, by the way, is because if we have poles in the right half plane, then our signals are going to go fly off to the rails, and that usually isn't useful. Alright, so this act of the signal being bounded by the rails is a nonlinear behavior that our amplifiers exhibit as they fall out of forward active. So linear control theory stops working well for them. Nonlinear control theory has some answers for us. And if you want to really formally describe how amplifiers behave, you can look up some fancy vocabulary words like limit cycles, Lyapunov stability functions, and describing functions. However, we're not going to do that. Our much coarser description of stability is that we can account for all the signals at the output in a stable system. So all the output signals are either at frequencies we put in or harmonics of those signals. So we're going to call a system unstable if it has some signal that comes out of nowhere, and especially if that signal comes out of nowhere when there's no input. That definition is pretty straightforward, which is good news. Finally, we often see instability when we're building open-loop amplifiers in the lab. For instance, really high-gain common emitters with long power supply wires can oscillate. But that's weird because those amplifiers are still open loop. We haven't introduced feedback yet to cause instability. So that oscillation actually comes from sneaky parasitic feedback loops that are introduced either through the power supply or through parasitics. So these parasitic feedback loops can cause instability even when you don't add explicit feedback around amplifiers, so always watch the behavior of your power supply and your layout when you're doing analog design, because it can cause instability. This, by the way, is why bypass caps are so important, because they make your power supply more ideal and prevent coupling paths. Alright. So now that we have a sense of what instability is, we're going to start developing a stability criteria for our transfer function. We're going to start by considering the feedback system pictured in the center of this slide. And we notice that it has the system transfer function that I've written on the left, or the closed loop transfer function I've indicated on the left. The first thing to note is that this closed loop gain is a transfer function, so if any of the roots of 1 plus L of S are on the right half plane, it will probably be unstable. It will fly off to the rails and start doing something nonlinear. Okay, that's fine, but finding the roots of 1 plus L of S is surprisingly mathematically tough. That's frustrating because we usually know the poles and zeros of L of S, but just adding 1 to it gives us a whole new polynomial that we have to find the roots of. So we're hoping to figure out if we're stable just by looking at L of S, which we know pretty well, without having to solve this whole ugly 1 plus L of S. We're going to start by noticing that if L of j omega is equal to -1, there's a pole on the j omega axis, and vice versa. Those two conditions imply one another. So L of j omega being minus 1 means this value will go to infinity, and because we're evaluating at j omega, that means the closed loop gain of j omega is infinity somewhere, which means this point j omega has a pole at it. That's an interesting fact, but we don't know for sure if the pole is currently, that's on the axis at this j omega point, will move into the right half plane or the left half plane as L increases. If it moves to the right, then L of j omega equals -1 is a stability criterion, and that criterion is called the Barkhausen criterion. However, poles can move either right or left depending on the specifics of the root locus, so you can't actually count on Barkhausen all the time. It's not a ironclad stability theorem, especially in conditionally stable amplifiers. That said, if we make a few assumptions about L, specifically that the phase decreases monotonically, then L of j omega equals -1 indicates a boundary between stability and instability. So we can express this L of j omega constraint in terms of magnitude and phase. So specifically, the magnitude of -1 is equal to 1, and the phase of -1 is equal to pi. And we can also notice that L of j omega is something that we could plot pretty easily. If we made a Bode plot of this, we could pick off these points where our magnitude is 1 or our phase is pi, and use that to identify how close we are to unstable. So, here's a Bode plot of the loop gain for a first order L of j omega. We can see the magnitude of the slope turn down at the pole location P and then continue going down forever. And at some point it crosses over the 0 dB axis here, and that point is called crossover. It's where the magnitude of L of j omega is equal to 1. Down here we have a plot of the system's phase, and on that plot I've indicated our stability metric, which is called phase margin. Phase margin is the difference between the system phase and pi, or negative pi in this case, they're the same number, at crossover. In this case, our phase margin is pi over 2. If the phase margin is 0, then we're meeting the stability criterion that we saw on the previous page, where we're at the border of stability and instability. Saying more than that requires us to assume a little bit about the behavior of poles, specifically that they're moving from left to right in the root locus. But if we make that assumption, then we can say that the system is unstable if the phase margin is negative, and stable if it's positive, and also that decreasing phase margin leads to more overshoot as the poles approach being purely imaginary. And that turns out to be true for lots of amplifiers, so phase margin is a good relative measure of stability. Now, one interesting note is that this crossover point depends on our feedback factor, which is part of the loop gain in this particular circuit. So as we change our feedback factor, this transfer function moves up and down, which moves our crossover point in or out, and can potentially change our phase margin. We're going to look at a few examples of open loop gains to get a feel for phase margin, and how we'd use it to analyze transfer function behavior. Here we're assuming that the gain stage, and first we're going to look at the open loop op-amp transfer function for an uncompensated op-amp. We're assuming that most of the dynamics for this uncompensated op-amp come from the gain stage, and that, like any other common emitter, it produces 2 poles. And this is often a good approximation for an uncompensated op-amp. We're ignoring the feed through 0 that would be up here for simplicity. 2 other details are important. We're going to assume that P2 is equal to 100 P1, which makes drawing the images a little bit easier. And we're noting that this open loop op-amp is in feedback with a feedback factor of f. So our loop gain is f times AOL. I'm going to show you the magnitude plot for this function in a second, but I'd like you to pause the video and try to sketch the general shape of this magnitude plot. Don't worry about getting it exactly right, because I haven't given you all the information you need to get the details the same as mine. This is a two-pole transfer function, so it starts at a value of fa down at dc, then it hits the first pole and starts decreasing at minus 20 dB per decade, and then the second pole and starts decreasing at minus 40 dB per decade, achieving crossover somewhere. Now, depending on what you assumed for FA, crossover could have been in this 20 dB per decade region or way further down. It all depends on the DC value of our loop gain. Next, we're going to draw a phase plot for this specific magnitude plot. So this one that I've shown, not whatever you have drawn. And we're going to try to assess the phase margin of this op-amp. You have enough information to make a pretty good drawing of the phase, so try to get the phase margin correct. Though I acknowledge that the lack of grid lines and numbers makes that job harder. So pause the video, try to draw the phase plot, and guess the phase margin. The phase plot will decrease continuously from 0 to pi over 4 decades, because the poles are separated by a factor of 100. The first pole is here, and we decrease by pi over 4 in the first decade, and another pi over 4 in the second. And the second pole is here, we decrease by pi over 4 in its first decade, and another pi over 4 in the second. So, straight line from 0 to minus pi because of this pole separation. And our phase margin is either very bad or 0. So if this amplifier is stable, it's going to be super marginal. It's barely stable at all. So uncompensated op-amps often have poor phase margin. Now we're going to try to find the phase margin of a dominant pole compensated op-amp. Here we're going to model the transfer function with one dominant pole. You might wonder where the second pole went. One argument I could make is the dominant pole is at a really low frequency now, so we're likely to cross over before the second pole matters, and I'm just ignoring it. And that would hold some water, but it turns out that dominant pole compensation also has a nice secondary behavior of pushing the second pole up to very high frequencies because of some impedance modulation. So this is actually a very accurate transfer function for a dominant pole compensated op-amp. Pause the video, draw the Bode plot, both magnitude and phase, for uncompensated loop gain, or for dominant pole compensated loop gain, and find the phase margin for this amplifier. The really low frequency pole causes our gain to roll off early, but because A is a big number, we're still probably not going to cross over until after a couple of decades. However, because this is a single pole system, our phase rolls from 0 to minus pi over 2 decades, and then just stays at minus pi over 2. So that means at crossover, it's easy for us to see that our phase margin is pi over 2, which means the amplifier is very stable. 90 degrees of phase margin is quite a lot. So in summary, for us, instability is getting a signal at the output that we didn't put there. Feedback through parasitics or supply coupling can cause instability. Phase margin is the difference between the angle of our loop gains Bode plot and pi, and minus pi, when the magnitude of L of j omega is equal to 0 dB. So distance from pi at crossover. And we pick that off from a Bode plot. We look at where the crossover of our magnitude function is in order to find the phase margin. And phase margin is a good measure of stability if poles are moving from the left-hand plane to the right-half plane. Phase margin greater than 0 is stable, closer to 0 is less stable, negative is unstable.